Okay, before we get to the remnants of a supernova, we're going to take a look and compare. Let me start this again. Supernova remnants. First, let's compare a supernova with a nova. One thing that all of these things have in common, a nova, a type 1 supernova, a type 2 supernova, is that their light curves are similar. They're going to peak in brightness very, very quickly in a matter of hours sometimes. And then slowly over time, they fade away. The light curves are the same shape, but the big difference is a supernova, as you can probably guess, is much more powerful than a nova. Remember, a nova is just a surface explosion. The supernova is the whole thing blowing up. So supernova, it's going to be a much higher light curve. The brightness is going to be much, much greater. Now, comparing type 1 and type 2 supernova, remember these are two wildly different things. A type 1 is when a white dwarf blows up in a binary, and a type 2 is when a very, very massive star blows up at the end of its life. And despite these very different mechanisms, their peak brightness is roughly equal. The energy level is about the same, which is kind of interesting. Type 2 are a little more common than type 1. We looked in the last lecture about how astronomers know whether it's type 1 or type 2 when it blows up. And there were a couple different ways to tell. The reason they're roughly equal, again, type 2 a little more common, but it turns out that almost all high-mass stars, certainly ones above 12 times the mass of the sun, and most of the ones above 8 times the mass of the sun are going to blow up. A very high percentage of them blow up, but there aren't that many of them. Whereas a very small percentage of low-mass stars are ever going to blow up, because remember, they have to be in that very particular situation in the binary and all that. So a very small percentage are going to blow up, but there are many, many, many more small, low-mass stars than high-mass stars. So it kind of balances out a bit. Okay, one final point here. The type 1 supernovae are actually quite a bit more important than the type 2 in the next chapter, because it turns out that they're more consistent in their peak brightness. That makes sense to me, because remember, they only blow up when the white dwarf reaches 1.4 solar masses, the Chandrasekhar limit. So every time it blows up, it's the same mass. Whereas the heavy stars that are going to blow up in a type 2, they can have a range of masses when they blow up. So they're not going to be as consistent. Why is this important? Well, if the peak brightness is the same every time, we can use these as what we call a standard candle. A type 1 supernova is a very important standard candle in astronomy. And that's when we use the inverse square law and compare the brightness. I usually use light bulbs as an example instead of candles. And to use the inverse square law, you have to make sure you're using things of equal brightness, like two 60-watt bulbs or two 75-watt bulbs. And so it's very important in the next chapter when we talk about measuring galactic distances that we have these type 1 supernovae to use for distance. So we've reached our final type of nebula. Let's recap very quickly. We have nebulae in which stars are born, emission nebulae such as Orion, the Eagle Nebula, the famous pillars of creation. We have some nebulae that kind of sit there in space and do nothing. The dark cloud nebulae like the Horsehead, and the reflection nebulae like the Witchhead, and they just kind of form interesting shapes. Then we had the planetary nebulae, which are one of the final stages of a star like the sun. After it becomes a red giant and it swells outward and the atmosphere starts to drift away, that's a planetary nebula. Beautiful ones like the Cat's Eye Nebula, the Ring Nebula, the Helix Nebula. We looked at a lot of those in the last chapter. Now we reach our final type, a supernova remnant, the leftover from the explosion of a star. And the one I want you to know, the most famous one, the most important one of all, is the Crab Nebula. One little reason it's famous is that it gets to be first on Charles Messier's famous list of objects. Charles Messier made a list. He was an astronomer in the late 1700s, I believe, or 1800s. And he made a list of objects that were kind of in his way. He was looking for comets, and he made a famous list. It's about 110 objects. And oddly enough, his work on comets isn't really remembered, but his list of objects that he wanted to avoid is still remembered to this day, and the Crab Nebula is number 1 on that famous list. The Andromeda Galaxy, for example, is M31. The Orion Nebula is M42, I believe, and so forth. Anyway, but what really made the crab famous, it's been famous for a long time because it was first seen exploding in the year 1054. And it was so bright it could be seen in the daytime. We had 2 stars in the daytime, which is pretty amazing. Everybody around the world, every culture around the world made note of this amazing explosion. To this day, 1,000 years later, we still see it rapidly expanding. So the picture I'm going to show you on the next screen is actually this explosion after 1,000 years, what it looks like. And with Doppler radar, we can see that it's still expanding very rapidly today. Now, that one was in our galaxy, of course, which is why it was so bright. But that wasn't the last one in our galaxy. There was one in 1571 called Tycho's supernova, after Tycho Brahe, who saw that one. And then Kepler's supernova in 1604. Both of those, you notice, are right before the telescope was invented. And since then, we haven't had one. And astronomers think that a galaxy our size, the size of the Milky Way, should have a supernova every 50 to 100 years. So we're really way overdue for one. We haven't had one in our galaxy since the telescope's been invented over 400 years ago. So we're really overdue for one. Hopefully in my lifetime, I definitely want to see one in the sky. That'd be amazing. Anyway, only time will tell on that. Now, the most nearby supernova in modern times is one we already mentioned, Supernova 1987A. But that one's not in the Milky Way galaxy. That one actually occurred in what's called the Large Magellanic Cloud, which is kind of a suburb galaxy of the Milky Way. So that one doesn't count on this list, but of course it became the most studied one of all time because it's the only one that's relatively nearby in modern times. There are only about 200 of these supernova remnants that we can see in our galaxy. Why such a low number? Well, partly because they're explosions. They're not going to stick around for long. They're going to dissipate pretty quickly as the gas and dust flies apart. So we've spotted about 200 of them. Let's look at the most famous one and the most, I think, important one of all time. There it is, the Crab Nebula. Crab Nebula. I believe this is located in Taurus. And that's what it looked like now, right now, after 1,000 years of expanding. That's what the explosion looks like. And there's going to be something inside that nebula that's going to be very important in one of the upcoming sections. And now here's another one that looks like it has dissipated more. Maybe it's older than the Crab Nebula, and you have these wispy trails of dust here left over from an ancient explosion. And then here's one, I believe this was the one, maybe the one just previous to the Crab Nebula that mankind got to see. And with modern instruments now we see the explosion. So it looks like it's still pretty compact. So maybe it's not that old, maybe only a couple thousand years old or something. And we'll learn more. Actually, I'm going to go ahead and do this one more section here about the heaviest elements. See, with the most massive stars, the type that go type 2 supernova, they build up to iron in the core. And we said that iron's the stopping point for sort of regular fusion in the core. And the core collapses, hits kind of a neutron brick wall, and rebounds and blows the star apart. What about all of the other elements? I mean, we have 91 elements that naturally occur on the Earth. There's actually one, if you're wondering, because uranium's number 92, and most people think there are 92. One of them we haven't found on the Earth yet. Believe it or not, of the first 92, little trivia. That one is called technetium, and we actually haven't discovered that in nature. It probably is somewhere in the core of the Earth. I'm sure it is. But of the 91 or 92 elements here on Earth, what about all the ones above iron? Where do they come from? Well, they're all created in the explosion of the supernova. See, regular fusion gets you up to iron. Now, regular fusion is what we say when you do hydrogen and hydrogen, or helium plus helium plus helium, carbon plus carbon. There's another type of fusion called helium capture, where, for example, a carbon will fuse with a helium to give you oxygen. Number 6 plus number 2 equals number 8. And then oxygen might fuse with helium to give you neon, which is number 10, and so forth. That's all kind of regular fusion. But what happens during the explosion itself, during the supernova, is when the heaviest elements, you see copper, gold, silver there on the screen, are formed in a process called neutron capture. It's not like regular fusion. Now, I don't want to get into all the technicalities here, but this all happens very, very quickly. And it's amazing that these rare elements are created all in those moments of the supernova. In the first 15 minutes, that's where these elements are all created, all the way up through uranium. The heaviest naturally occurring element. Now, in a lab, of course, we've made elements heavier than uranium. But in nature, that's how they're all made. It's really, truly amazing. That is the only time that those elements are made, in the first 15 minutes of a Type 2 supernova. Really, truly amazing. Finally, let me just mention this. Back at the beginning of stars, towards the beginning of time itself, at the beginning of the universe, the first generation of stars, the only elements in the universe at that point were hydrogen and helium, maybe some trace amounts of lithium. That was it. All of these other things did not exist. And so what happens is, with every generation of stars, more of these elements are created and spit out into space, and then new stars form from those elements. So this gives us a way of doing a timeline to know the age of a star by what percentage of that star is composed of heavier elements. Because the more heavy elements it has means it's from more modern times. You see, the first generation of stars would have a very low metallacity, we call it. They would just be hydrogen and helium, and that's about it. But a star that's born today, let's say in the Orion Nebula, it's going to have the highest percentage, the highest metallacity of any generation of stars. Those stars in the Orion Nebula today, because they're born from material that has been created and blown out into the universe for the last 13.8 billion years. So you can look at the metallacity of a star to give you some idea of how old that star is. And we'll do a little more next time. Thanks for listening.